Okay. All right. Shall I begin? So let me share my screen. All right. Can everybody see this? Okay, cool. Please let me know if there's any problem. For example, if you cannot see that. All right. So hi, I'm Andy. Oops. So as a psychology student, I've always been interested in how the human brain relates to an AI. For this course project, I selected a computational neuroscience paper on human reinforcement learning. So let me briefly introduce the paper I selected. The authors conducted a hierarchical two-armed bandit test while recording human brain activity with fMRI. So each trial begins with this top-level blue and yellow stimulus, and if the participant presses the left button, then 70% of the time the purple stimulus appears here, and the remaining 30% of the time the red stimulus appears here. After this transition, the participant makes a second choice and then receives a monetary reward of either 0, 10, or 25 cents. So the authors proposed three human reinforcement learning algorithms, SARSA, forward, and hybrid. Let me begin with the first algorithm. SARSA is a model-free learner, which means it does not try to understand the structure of the environment. Instead, it simply updates its action values using reward prediction adders. In short, SARSA learns directly from experience. The second algorithm is the forward model, which is fully model-based. Unlike SARSA, the forward agent tries to learn the transition structure of the environment. It estimates the probabilities of moving from one state to another and updates these probabilities using state prediction adders. And finally, the authors combine these two systems into a hybrid agent. This model mixes the two value estimates, like the model-free value from SARSA and the model-based value from the forward model. So the authors reported two key findings. First, the hybrid model provided the best fit to human behavior, showing the lowest likelihood and AIC value, and SARSA performed similarly but slightly worse, while the forward model showed the poorest fits. Second, fMRI results revealed that the brain regions associated with both reaction prediction adder and state prediction adder computations were simultaneously active during the task. So this suggests that humans actually rely on hybrid strategy that integrates both model-free and model-based learning. So this brings me back to my research question. So if humans use the hybrid model, does it also learn best when implemented as an artificial agent? So to evaluate these models, I recreated the same task in Python and implemented all three agents following the learning rules described in the paper. So each agent interacted with the environment for 10,000 episodes, and I repeated this process with 10 independents. For every episode, I recorded the total reward the agent received. Then, to make the learning curve easier to interpret, I averaged the rewards across the 10 runs and applied a 100 episode moving average, which smoothed out noise. So the results closely mirrored the behavior findings in the original study. SARSA and the hybrid agent learned quickly, like here, orange and green lines. Um, while the forward agent learned much more slowly, taking many more episodes to reach its asymptotic performance. So, however, the hybrid agents did not outperform SARSA. Their learning curves were almost identical. So this suggests that while humans rely on both model-free and model-based computations for flexibility and planning, the added complexity of the hybrid model does not necessarily translate into better performance in simple environments. So several extensions could build on this work. So first, I only test a simple hierarchical bounded task, but more complex environments such as like multi-step decision task or stochastic grid words may reveal clear benefits of model-based or hybrid research. And second, my current implementation use tabular RL. In future work, probably I can develop into deep reinforcement learning by developing like deep SARSA or deep forward or deep hybrid model like DQN. All right, so that's all for my presentation, and I'm happy to take any questions from you guys.
Yeah, so one of my questions was, so with the hybrid model, it's like the
Hmm.
weighted average between both your forward and the SARSA model. So it has like the WT parameter, I think. Yeah. So
Yeah.
why do you think that as your model like went through your epochs, or I forget what their episodes, that it went more towards the SARSA model, even though the forward model was producing a better output?
Oh, actually, Ford model didn't produce better output. Well, it was actually the poorest, and it's kind of interesting that I think like hybrid model could be somewhere between Sarsa and Ford if it could not like outperform anything, but actually it was like very similar to Sarsa, and I think
Hmm.
it's quite interesting point because it's not somewhere between, but it's really similar to one model. And I think it's because I don't know, to be honest.
Okay. Yeah. And then also with kind of going off of that, um, so you said like with the brain activation regions, it
Mhm.
used kind of both the state and the reward. So you're thinking that's what like the human is. I was thinking like kind of is that you I don't know if you actually saw this thing, but like between the relation of like the like quote unquote like strengths or like how much it was taking from a state prediction versus a reward prediction, did you see a similar that versus like kind of how it took from both like the forward model and Sarsa or like in like their predictions, did it predict more? Because with these values it seems like Sarsa is predicting better. Did they also see that there was more activation in the brain pathways where it was focusing more on the state than the reward?
I don't think they stated like um, SARSA, either SARSA or Ford model activated more or stronger activation in the brain, but they
Okay.
just stated like brain regions in terms of regions, not magnitude. So
Okay.
it's really hard to tell that
Yeah.
one. Yeah.
I'm not, yeah, I have
Yeah.
nothing, no knowledge in the brain stuff, so
No, it's
but
fine.
yeah.
It's for your interest.
Yeah, that
Yeah.
was a cool presentation.
Cool. Thanks. So it's a second presenter from 37, 2008. Oh, it's actually second presenter starts from 241, so I can take more questions unless the second presenter wants to start earlier.
I'm the second presenter. I could.
All right, cool. Thanks. Please give your speech.
Sure. Let me get that set up. Okay. Can you see this? Okay.
Yep, I can see that.
All right. Um, so My track was a project's mini recreation. I followed a study done by Arnold K. Griffith, which checked alpha beta pruning across multiple different random trees and showed how it can make a chess engine work better. Now, to understand my project, you have to understand what exactly that means. And so let me explain how a chess AI works. Well, the primary method is called minimax. What it does, well, chess, you have to know to implement minimax. Chess is a two-player, zero-sum adversarial true information game. Basically, what this means is there's another player who whose results compare to your results. So if you win, he loses. If you lose, he wins, or there's a tie, and he's trying to beat you. The last thing is true information. Everybody knows all the information about the game. This allows you to predict what your player that you're playing against is going to do. So let's take a chess position. Uh, I will use this chess position as a baseline to help explain this. So, how does Minimax decide the best move? Well, naturally, it predicts the best move by assuming that your opponent will also play their best move on their turn. If you play a mistake, you have to assume that your opponent will capitalize on it. So, you have to we call yourself the optimizing player, the person who makes the best move to make the position the best, and the opponent is the minimizing player, the person who makes the position the worst for you. Well, how do you evaluate the position? Well, we give each piece a point value. Pawns are worth 1 point, bishops and knights are worth 3, rooks are worth 5, queens are worth 9, and the king is worth the entire game. If you lose the king, you lose. So let's make it 200 points. Also, we'd like to give adjustments to pieces that are more useful. So we add a few amount of points per each move that a piece can make. So in this example, white has more points, so we are black since it's black's turn. The total is a minus 1.3 points. However, in this position, this is actually a checkmate and 4 for black. So the position is deceiving. Why is this position worse for black than it is for white? Well, that's because white is looking 0 moves ahead. To find the proper position and how beneficial the position is, you have to look more moves ahead to see what the positions could be. But that brings a problem. What is the opponent's best move? Well, it depends on what I'm going to play after that. Well, what am I going to play after that? Well, it depends what the opponent plays after that. You can't just keep looking deeper and deeper forever. There has to be an end. So at the end, you pick the best move by the best position after a certain depth. And the depth is how many moves you will look forward to evaluate the basic position like this. So, uh, what I'll walk you through kind of how it works. It will find the best, or it'll find the engine will search until it finds a piece for black. Then it'll find a move for black and check that move. It will then find a piece for white, and then at a depth of 2, it will find all the pieces for that move, or all the moves for that piece. It will evaluate these positions to see which one's better or worse, then it'll move on to the next piece. Now, pieces like pawns are not problematic because they have mostly moves of 1 or 2 at a time, whereas queens can have multiple moves. This causes lots of branching. And if you look at the total amount of moves that are in any given position, the amount of branching starts to snowball. And after the engine evaluates all these positions and all these moves, it goes back to the first piece and it has to evaluate the second. And then it does that for every black piece. So this is just a depth of 2. To solve this chess puzzle, you need to go queen takes f2, rook takes f2, rook d1 check, rook f1, rook f1 checkmate. That is 5 moves ahead. To do this, you would need to implement something called alpha beta pruning. What alpha beta pruning is, it cuts off moves that don't make sense. Alpha keeps track of the best possible position at each depth, and beta keeps track of the worst possible position at each depth. So basically, if white finds a move that black can make but will result in a worse position then a move it is already made, then black will not make that move because it is just already worse. So if white can find a move that black will make next turn that will result in a worse move for white, then white will not make that move because it shouldn't allow black to get a better position. So now that you understand what is happening, uh, I can show you my results. So how did I test these results? I created random trees. Chess is too large, too many branches, very slow. So what I did is I randomly generated trees with different values, and uh, I found the best position using a minimax search. Then I implemented a alpha beta pruning to find if it, to see if it could find the same best value without losing any efficiency. So as you can see through these graphs, the results show that the nodes evaluated by the pure minimax solution was much, much larger than the alpha beta pruning and grew much further as branches increased. To compare the results, you can see you can ignore the uh, predicted results. If you look under alpha beta and the far right, you should see that these kind of line up, and minimax will always be the same because it checks every branch in the tree. And to test it with actual chess, I had to program all of actual chess, and these are my results. As you can see, many of the alpha beta testing tested many fewer nodes, and sometimes it got cut off with the branching because it just took too long. So some of them are tied, but both of them only failed one test, and that's because the depth was too high. All right, that's all for my presentation. Any questions?
Oh, cool, cool. Well, let me give you a light question. So, do you actually play chess?
I do, I do.
You do?
Yeah.
Cool.
I'm not very good. My chess.com rating is like 1,200.
Oh, well, that's nice. Cool.
Do you play chess?
I once played like a couple of years ago, but I almost forgot everything. Oh.
Yeah. I mean, I played a lot as a kid, but as an adult, I'm smarter now, and if I played more, I feel like I would be a lot better.
All right. So why did you like what did you say? Why alpha beta pruning is needed in comparison to minimax?
Yeah, so alpha beta pruning, let me go back to this example. So
Mm,
the positions are, well, as branches in, like, if you keep going further, there's more branches, and you want to cut off branches to evaluate less positions.
right.
So, uh, alpha beta pruning is basically, let's say, oh, this is a bad example because it's a checkmate, but let's say black makes this move, which is checkmate, right?
Uh-huh. Yeah.
This this is the best possible move that I can make, but let's say there's a better move that black hasn't evaluated yet, right? Let's say there's a move that makes me get checkmate and the opponent has to give me $5, okay? And I haven't
Hmm.
figured that out yet. So, white is gonna say, okay, if I play this, black gets checkmate, right? That is the new alphabet value. So now I'm if I play something else, like let's say the pawn moves here, right? And then black doesn't get checkmate, then I would play that move instead. But let's say uh I keep I move here and I keep looking for moves and magic move rook here moves here, right? And the opponent has to give me $5. Well, the I don't have to evaluate any more positions because this position is now better. Actually, sorry, I got that backwards. Let's say this position made me win $5, and then this position where the piece magically moves and checkmates doesn't give me $5. I would not need to evaluate that position further because it is not as good. So I wouldn't evaluate. This is such a bad example, but I wouldn't evaluate this position further. I would
Hmm.
evaluate this position no further because I already know that this move creates the worst possible move. So I can block that. However, in this puzzle, it doesn't work because this is a bad example again because this position is forced checkmate. So no matter what, white loses. So it's kind of hard to make an example with this, but um, I guess I don't know if you understood that.
Yeah, I got it. And I have one simple question, one simple short question. So
Mhm.
why does the queen worth like 9 points while rook is 5 points? Like, is there any
This
reason behind it?
Yeah, this was not decided by me. This was like actually a national chess convention that like all the best chess players do to evaluate positions. So
Mhm.
these are just like standard 1, 3,
Um,
3, 5, and 9. Although although the new standard is bishops should be like 3.2 and knight should be like 3.1, but just for simplicity, I left it like this.
cool. Thank you. It was great talk.
All right, thank you so much.
I have a quick question for you. Can you hear me?
Oh yeah.
Perfect. Uh, Oliver, really nice presentation. I'm kind of
Thank you.
curious, did you try to compare these two performance, like min-max and alpha beta? Did you try to play a game and compare this, like not the time, but like actually which one have a better like algorithm that do good? Like,
I I did. I tried to do it with chess positions,
uh-huh.
right? I would give it chess puzzles on chess.com, and it certain chess puzzles require too many, like too much depth, and it would take forever. So
Okay.
like it would I wanted to do this whole presentation on just chess puzzles,
Uh-huh.
but because each puzzle was taking like upwards of 2 hours, I had to
There.
I had to switch and do it with random trees. So
Gotcha, gotcha. Okay, I see. Thank you.
mhm.
Well, I can start. I mean, it's 2:50, a little bit past. I think I can start if there's no other questions to ask. I
I
mean,
think we're ready.
perfect. Let me share. All right. Can you see it? I think so. Okay. Okay, I will start. So, well, good afternoon, everybody. Welcome to my presentation for this course project. So my project is titled Physics-Constrained Neural Network for Design Space Optimization of a Vein Pump. So to give some context, vein pump, which I'll show here, introduction. So vein pump plays a major role in hydraulic industry. It is a critical component in many field application, including automatic power steering system, transmission, marine uses, and also if you drive, you go to gas station, most of the gas pump is used using vein pump to produce. So vein pump have really good volumetric flow rate in comparison to other pumps, so make them a good advantage for large flow processing. So however, the engineering goal for having those pumps, of course, is to design those pumps to maximize the performance, both volumetric efficiency and hydromechanical efficiency, but of course, to ensure durability as well in the process. So however, because there's such a huge amount of parameters was being accounted in a vein pump, the optimization is very difficult for engineering because a lot of aspects should be considered. So traditionally, CFD simulations were just mainly used to testing the performance of vein pumps design. However, though they have really high fidelity, the limitations are it takes hours for per run. But if we want to optimize, for example, the geometry, for example, if we change veins size, let me see if I can. Do I have pointer here? Yeah, let's see. If you want to change a vein size or any of those pocket size to see if we can improve a certain aspect, it takes like hours to decide whether one geometry is good. And if we want testing like hundreds of geometries, that's gonna take too long to do. So simply for the modern optimization process, the CFD is really slow in comparison. So with that, one possibility, so this is kind of why I want to introduce machine learning, because machine learning have a great way to predict stuff while with enough of data, it can produce accurately, but also in a faster way. So the model I'm using to train this machine learning is a numeric model. This model is shown on the second portion. It's a multi-domain physics solver. So originally CFD is only in computation fluid dynamics, which only consider fluid. However, this model, which is built through our lab, we consider geometry modeling for which is what the optimizing. There is a fluid domain, so kind of showing here, and then it's testing fluid mechanics and film mechanics. But also it considers force module and the motion module. This is solid body dynamics. So this is kind of a coupled a simulation with both kinematic fluid and the mechanical dynamic body dynamics. This project oriented in hydraulic circuit, which is the fluid portion. I purely want to know what's the volumetric flow rate. I'm less concerned with the hydromechanical. So that's that the lumped parameter model uses to predict the volumetric efficiency very well. And also this model has been verified with our reference machine to ensure that the performance is close to the result is within about 1% of the deviation. So with that, I've been using this model's result kind of to train the model that I will build for this optimization, right? So going to methodology, I kind of show a little bit in the introduction side, but why do I choose a physics constrained neural network? So physics constrained, the loss function have total will be equals to the data, first the data loss, and also the PDE solver, which is the physics that's used to governing the equation, right? The physics layer I have okay. This is kind of the equation I'm using. You consider how much is flowing, how much is flowing out, and then there's how much was the leakage. And with that, you can, with the theoretical flow rate, you can get a efficiency by total loss function kind of showing here. So going into the result, why do I use physics constraint? So you show in the first round, I have some inlet flow, what are the leakages, and what is the outlet efficiency. So you kind of see that the points, which is the result testing. So I have I have some left out data that I used after I trained the model. You can see it predicts relatively close to the ground truth. First compare to some standard neural network model, MLP. You can see that without the physics layer, which is considering the leakage and those aspects, the prediction is not really accurate. They tend to hallucinate a lot and sometimes goes to negative flow rate, which is certainly impossible because that kind of violates the mass transfer. Like the outlet flow is higher than inlet flow. That's just certainly impossible to achieve in physics world. In addition, to compare this PCA model with the numeric model, I know that my numeric model does not need to train, but then the solving time is usually around 2 hours-ish to finish. However, compared to with 1 hour. For a PCA model, it does take larger training time, but then we're actually solving for the geometry, for different geometry. It's very fast to give me the result. This is really good for a fast, rapid pump optimization, right? It also produces relatively good result. So kind of to conclude, this embedded physical constraint for the neural network architecture eliminates the physics violation, like unreasonable mass flow rate, but also with sufficient amount of data, it trained this model well that can enable rapid pump design for the geometry. And then some future work would be, of course, incorporating more parameters that being considered, so they can enable more feature optimization and also validate them, but that will be a next step. Right, so that is all for my presentation, and I will take any questions. Thank you for listening.
Yeah, can I first ask what your major is? I'm kind of curious.
Oh, mechanical engineering.
Okay. So, you said you had three coupled modules, right?
Yes.
Could you explain to me how those, can you walk me through those and how they solve the physics problems?
Okay. All right. I think I just canceled the sharing. Let me reshare it again. All right, here we go. All right, that's a great question. So first, you have this pump, you have a design, right? When you have a pump, pump's geometry, I call this lumped parameter model because in a traditional CFD, you solve in a molecule level. But then in a lumped parameter, you assume you lump the molecule basically. So you can see this each chamber. So each between these two veins, this chamber, I assume they're at its equilibrium, which means I assume this one single chamber as one volume that have it's the pressure and the fluid property is equivalent across. So with that, the geometry. So I have from CAD drawing to geometry model, which means that it calculates at each angle. Like refinement can be defined, but at each angle, the geometry, how much volume is inside is being calculated. Also, how much to simulate pump, you need a pressure buildup equation or like a orifice equation for the flow rate, right? So at each second, you are able to know how much is the opening, which means how much orifice is how large is the orifice for the fluid to flow into the chamber or to flow out of the chamber. So those are calculating the flow rate. So those geometry model is very important to kind of the foundation of the simulation. And then you have this fluid dynamic model, which first including what I just said, pressure buildup equation and how much is flow is being used. And also the gap model, it means, so in a pump, when they simulate for the hydromechanical efficiency side, you know that pump usually pumping oil. And then the lubrication, which is a film is a huge aspect on the efficiency of the pump. So like the film, for example, between this rotor and the casing, right? This film is also an important part to be solved. And with those fluid being solved, you give a pressure, fluid in pressure, right? So
Okay, I
I need to
see.
speed up. And then the force, it convert to force to see the body dynamics and how those body moves, which means how leakage is caused, because if a shift eccentricity will causing drop the flow, because body cannot be there always a clearance, and things cannot be in the state you wanted typically.
I
Yeah.
see. I see. That's very interesting. I like the inclusion of the gap model for just in case.
Okay.
It's very
Thank
cool.
you. All right. I think I'm running a little bit longer, so I will stop and then let the next person to present. But thank you for the question.
Of course.
Can everyone see this? All right.
Yep.
So today I'll be discussing a reproduction study of a 2019 paper on a data augmentation and regularization technique called cut mix. So this is the original paper, and the authors claim that cut mix consistently outperforms the state-of-the-art augmentation strategies on CFAR and ImageNet classification tasks. And this is the core claim that we sought to verify. So first, what is data augmentation? Well, data augmentation means that we modify the input images to artificially increase the number of training examples, and the hope is that by showing the model a greater variety of training examples, we can combat overfitting. So that's why we say that data augmentation strategies can act as regularizers for convolutional neural networks. Now, on the left, we have pretty standard augmentations. These are random crops and horizontal flips that are very common in the literature. So this is a good baseline against which we compare our stronger augmentation strategies. Next up, there's mix-up, where we linearly interpolate between two images and then mix the labels in proportion to how visible each image is. Then there's cutout, where we randomly remove a square from the image and replace it with zeros. So this works kind of like dropout, except it operates on the input image instead of the hidden layers. And then finally, there's cut mix, which combines ideas from mix-up and cutout. So like cutout, you remove a random box from the original image, but instead of just leaving it as zeros, you fill that area in with pixels from a different image. And then like mix-up, you mix the labels in proportion to that visible area. And the authors claim that cut mix will outperform these other data augmentation strategies. So to test that, we use two data sets, CFAR 100 and Tiny ImageNet. And we test across two different models, with ResNet 50 being our larger model and ResNet 18 our smaller model. We test all 4 augmentations, and within each experiment, we keep the same optimizer and training schedule, so only the augmentation is changing for a fair comparison. So here are the results on CFAR 100. Cut mix outperformed all the other augmentations, reducing error for ResNet 50 by 4.23%, and reducing error for ResNet 18 by 1.75%. And notice that the larger model actually benefits more from the regularization, like we might expect, since larger models are more prone to overfitting. And this data supports the author's claim that cut mix outperforms the other augmentation techniques. And here I've got our results on the left and the original results on the right. So you can see that the relative order of the different augmentations is preserved in our reproduction, with cut mix doing the best, then mix up, then the baseline, and then cut out last on the top one error just by a small margin. Now, unexpectedly, in our experiments, cut mix underperformed the baseline on Tiny ImageNet, actually increasing that top one error by 0.66% for ResNet 50. And this was surprising because we used the same model with the same training schedule and hyperparameters that work so well on CFAR 100. And compared to the original paper, we actually saw this reversal here where cut mix underperforms the baseline. I think the key difference here and why it didn't work is that we're using Tiny ImageNet, which is a downsampled subset of ImageNet instead of the full ImageNet dataset. And in many ways, Tiny ImageNet and this image classification problem is actually a harder task, with most CNNs performing worse on Tiny ImageNet than the full ImageNet dataset in the literature. So the regularization effect of cut mix may have actually been unnecessary here and seems to have hurt learning in our case. So in conclusion, cut mix can boost image classification accuracy. We saw that clearly with the CFAR 100 dataset on both ResNet 50 and ResNet 18. But it seems that hyperparameter tuning is important and dataset dependent, which might explain why cut mix actually underperformed on Tiny ImageNet, even though we were using the same hyperparameters that worked on CFAR 100. So this tuning might mean applying cut mix less frequently in training to allow the model to see more unaltered training images, or cutting and pasting smaller patches from the images so that more of the original image is visible to the model and less is occluded. But overall, our reproduction supports the author's original claims that cut mix can be a useful tool when training CNNs for image classification tasks. So thank you, and I'll open it up to questions.
All right. Hi, Ryan. Nice presentation. So my first question is kind of a more general question. So what are the applications for this kind of model? Like, what do you see, like yeah, what kind of application and where should this be used?
Yeah, so this is pretty broadly applicable to most image classification tasks, including transformer networks. So I didn't discuss transformer networks here, but there are versions of cut mix that have been used with the newer vision transformer models that can boost accuracy quite a bit. And like these data augmentation techniques are, one of the good things about them is they are very broad. So just about anywhere you're having trouble with your image classifier overfitting significantly, this might be something you can just drop in and try.
Okay, gotcha. Makes sense. Thank you. The second question, I guess. So you kind of present how do you evaluate this the accuracy? By that I mean like is it like how you like I take that if you have some overlay image, your goal is trying to restore to its original state. Is that the right way to interpret it?
Well, maybe I should make this more clear. I should have mentioned this in the presentation. We only apply the augmentations to the training. So we're actually evaluating, it's just like a normal image that the model is seeing. And then during training, the way we evaluate it with these mixed labels that you see here is we used like a modified version of categorical cross entropy, where you can, instead of having like, one like hot encoded like one and then a bunch of zeros, you just use like the labels, I guess. So you see like 0.5 for convertible, 0.5 for goldfish, and a bunch of zeros for all the other classes. Does that answer your question?
I think so. So it's more like a object identification, like class 2 for the
Kind
image,
of. So
kind of.
it's still image classification because we're not assigning bounding boxes. But one of the interesting things the authors found is that when you do this process, it kind of forces the model to learn to focus on different parts of the image, and it does kind of learn object detection almost as a byproduct of this. And you can construct what are called class activation maps to see where the model is looking in the image and put bounding boxes around it. So it's kind
Okay,
of a
okay.
neat byproduct. Yeah.
Yeah, makes sense. Thank you.
Yeah. Any other questions? Okay. If not, I think I'll turn it over to Zach.
Yeah, what a transition. Okay, let me share. Do okay, that should be. I'm gonna get this full screen. Okay, hopefully that's good. Uh, so my project was doing machine learning on NFL games, so trying to predict the outcome of NFL games. And this was kind of a mix between definitely not gambling, but a mix just between like a fun thing that I could do where it's like a real world application of some of these machine learning things where there's a lot of data out there and there's a lot of different methods you could go about doing it. Um, so I was going off of initial paper, and this was the paper was more or less going through different machine learning methods. So it was going through like you have your naive bias, you have your or like regression models, gradient boosted trees, stuff like that. And essentially, it was taking in 21 different parameters based on play-by-play data. So stuff like passing yards, rushing yards, touchdowns, that sort of stuff and taking in all of those past like season averages for that team and the historical averages for the league and taking that in so it was something like 82 parameters into and tabular data and feeding it into these machine learning models, doing some basic hyperparameter tuning and then getting the output. So they were getting pretty good results. And I was like, okay, that's like a decent bar. I think they were getting around like 67.5% on their like best model with hyperparameter tuning. So that was kind of my little quote unquote like threshold is if I could get a similar response to this with my hyperparameter tuning and adding more features, that's kind of where I want to be. So initially, my first result, I think it was like 55% using the exact same methodology they were using. So while they were getting like mid 60s to low 60s, I was getting like mid 50%. And I was like, okay, like it must be some stuff with like the features or something. So I tried like re-engineering all of them because I was doing it manually using their data set and still I was just not getting anywhere close to their results. So I really don't know what was happening because I was always hitting the softmax around like 55% no matter how much hyperparameter tuning I did or like feature selection I did. So I was kind of looking into doing more nuanced feature selections. So they were having both historical averages and the individual player or like team data. But I think part of the problem was that most of these like simpler machine learning models didn't actually see the relationship between that. So if you have one feature being, oh yeah, passing yards, and another feature being historical league average passing yards, it doesn't necessarily make that connection. So one thing I was trying to do was add a normalization feature. So I normalized all the passing yards. So let's just say like team A normally lets up like 300 passing yards a game, but team B normally lets up 200. So if you pass for 400 yards against team A, that's less impressive than passing 400 passing yards against team B. So I added some basic normalization based on this, where it just like updated their game statistics instead of just their raw value, a normalized value. I just actually moved it up from like the mid 50s to like the high 50s. So I was like, okay, that's pretty good. We're on a good track here. But again, that kind of like capped out at around like, yeah, 58, 59%. No matter what I could do, what I did, nothing was getting above that. And then I was kind of like, okay, it's not doing that great on these complex tasks. Because there's a lot that goes into an NFL game. It's not just 20 stats or whatever. That's like your win or lose. So my next idea was doing something where instead of saying, hey, here's these like 20 stats, or I think I was like my feature space was up to like 100 or 150, because I was encoding a lot of different play-by-play statistics. I was like, okay, we take this 150 feature set data, which has a lot of more niche stuff, like, oh yeah, like how many passing yards do they get like to the deep left field every game, stuff like that. Because that doesn't necessarily correlate to a win. That might more correlate towards like something like passing yards or passing touchdowns. So what I did was instead of doing one big model, I changed it into 21 individual regressor models that then predicted, hey, how many passing yards are they going to get, how many receiving yards, like rushing touchdowns, stuff like that, and then use those 21 parameters or features and then fed it into a new model that then says, hey, if you have 200 passing yards, your opponent has 300 passing yards and 5 touchdowns, who's going to win that game? And that actually worked pretty well. I think my first, without any tuning or whatever, was like 65%, which is already better than the baseline I was hoping for. And doing some hyperparameter tuning, it ended up being a gradient boosted classifier was like the quote unquote best model for this. This because I think that's whatever most for tabular data, the most common output is gradient boosted classifiers or regressors. But yeah, so on the top right, we could kind of see, hold up, if I could zoom in. Uh, I hate, please. Okay. So this was kind of like a heat matrix of what what parameter each one of these used. So I had 140 input parameters and was kind of making the scale down nicely. But so you can see like with the screen, it's a lot of like what parameters were using the same features. And then so we see like some between like passing yards and passing touchdowns and passing yards and like pass or and like completions, passing yards, stuff like that. But things like extra points made in passing completions don't really have anything in common. So that actually allowed it to like find more niche connections between or complex connections between the large feature space and the end model. So running this on actual like NFL data, it actually did decent. I mean, better than I thought it was going to be for a machine learning model. Because like the 70% test isn't necessarily mean you're going to get 70% in real life. I think this past week, so like here we see kind of improvement over like week by week and see that like every week it's kind of learning based on the normalization and improving its accuracy. I think this most recent week it predicted 75% correctly, which was like probably better than most of it, which is still like decent, but it's still not, I want to say, gambling material. Um, but yeah, so I kind of made, I don't really know what track I was going. I kind of did a mix of both, but I made like a UI that's just like, oh yeah, all the teams where they're gonna win and some of the stats that are like important. So yeah, that's kind of my thing was that if you have a very large feature space, splitting it up into smaller models instead of trying to predict on like 100 to 200 individual tabular features could give better results, although it might have a higher training cost. And yeah, open it up for questions.
How far before kickoff are your features available? Like, can I predict this a week in advance or a few hours in advance?
Yeah, so I mean, so for the whatever, I have it scrape update with the past week features on Tuesday, so it'll be ready like available that like I think I set it to like Tuesday at 2 a.m. because I'm running this for myself. So I have it go out and scrape all these features, then update everything. Um, but yeah, so pretty far in advance, and that was one of the things where it was like um there could be other room for improvement based on like weather data or like injury data that I haven't done that might not be available at like that Tuesday value. That was too complex for this class, so I was like, let me just do basic features.
So are you saying that you did not test it with gambling?
No, I was gonna go through and actually look at the stats or like the because predicting a simple like money line winner isn't necessarily always like it's not always 50-50. Like 75% doesn't mean I'm gonna make like 25%. I think I was looking at it
Mm-hmm.
this last week and I think I would have lost if I bet like $1 in every game, I would have lost like $3, but it's
Mm.
fine. It's fine. But yeah, do you have a question?
Quick question. So, did you see, or do you think the performance will improve as the season goes on because then you have more data to train? Since like it's difficult for this kind of prediction to use previous years' data. Is that
Yeah,
correct?
so kind of what I was seeing was with the normalization, it allows Or like, and as the year goes on, there is like the quote unquote like regression model trained, like this red line there that shows the improvement. I'm not sure how accurate that actually is, but it is cool to see. Like when teams had like bad streaks, I think like the Bears were something where it was like at the beginning of the season they were like actually like, or they were like okay. I don't forgot their record, but they weren't, their stats weren't like very impressive. But like as the season went on, it predicted them to like win more and more games. Um, because yeah, I think it had him beating like Philadelphia this week, and like a month ago, I'd have been like, no way did he beat the Eagles. Um, but yeah, so it's kind of cool to see. It does improve slightly week by week. I'm not sure if that's just the games have gotten more diverse, or if it's actually that it's learning something.
Cool, cool. And if you don't mind me ask, what happens at week 10?
Hold up. Let me actually. I thought the same thing. Let me actually go through and I could probably pull it up. Hold up. How do I stop? Actually, I think we might be going over, but it doesn't matter. How do I get out of this page? Dude, how do you, anyone?
Yes, see?
No, it's not working. Um, hold
Huh.
on, let me like move this
Are you
top.
considering a career in like sport gambling? Because
Um,
that's blowing up right
honestly,
now. And there are a lot of companies. I'm sport engineering and AI,
okay,
and
yeah.
there
So I
are
was
a
gonna respond to
ton
your
of
message after.
companies
Yeah,
that I think would be a really good fit for you, or vice versa.
yeah. I would say my I don't want to be like my dream job is to work at like somewhere doing like the betting lines and stuff like that. But I feel like if I ended up there, I wouldn't be mad.
I mean, you
Um,
could leverage that for scouting, right? Like,
yeah.
are you from Indiana or would you stay here?
No, I'm from like outside of Chicago. So
Okay, so not far,
yeah.
I guess. There is a company you might want to look into called Telemetry. I'll drop their
Okay.
stuff. If you like them, send me an email and I'll send you the contact of the person you would want to talk to get in with them.
Okay.
But they're doing a lot of stuff like this to help scouts make better decisions.
Okay.
So you
Yeah, no, so
could, I guess you could look at it as the dark side, but there are other
yeah.
ways you could flip it.
Yeah, no, because or like in the I do a bunch of like March Madness stuff, so like that's another like other in the fall I was doing this, in the spring I go to do basketball prediction stuff. But yeah, I don't know. I enjoy it.
Here we go.
Hold up, let me see. Oh, there's the X. Okay. I think I have it up here. If I go week week 10? Uh you guys could see this, right?
Mhm.
Okay. Why is it?
Is this yours?
Yeah, this is what AI made in like 10 minutes because I was like, I don't know what project track I should be on, but this is
Oh,
my like
How did I draw
quote
that? How I get
unquote
a
product.
yo, I had the same issue. Um,
Oh, why is it taking so long?
I went to the inaugural TED Sport conference this year, and there was an entire like block of talks on sport betting, exactly what you're talking about.
Yeah, I feel like part of it like is that there is a problem just because like I feel like gambling as a whole is not good for the sports industry. Um but that's a whole I do it for my
Depends on who
enjoyment.
you're considering the end user to be and like the key stakeholders. It could be, it could not be.
Yeah. I show up. Did this do better than I thought? I think I might have accidentally oh no. Yeah, part of this is it loves Minnesota for some reason. I think it's predicted Minnesota to win every single week, and they're like what 2-9. It might be because they had like a strong start of the season. But so what? This game is right. The second one is right. This one's right. This one's right. This one's wrong. That one's wrong. This one's right. Like it loves Carolina, and like I don't think they've ever like I don't know.
We get some love for the Cowboys.
Yeah, but the Cowboys are like, where's the Cowboys game at?
I don't see them.
Oh, because they're on bye this week. Like what?
Okay.
I wasn't just excluding the Cowboys. Um, but yeah, like some of these games, like Houston was correct, Seattle won. I think the Rams won this game. Yeah, Washington lost, got like blown out by Detroit. Chargers won, and Green Bay lost. So it's like stuff like this where it's like kind of it's good, but it's not like great. I think is the thing. Which is where all the optimization comes in, where if you could like cross that like 75, 80% threshold where it's actually like makes you money. I'm not there yet. But yeah. Any other questions? And I'll check out the one telemetry thing.
I'll find the other companies. I'll look through our stuff,
Okay.
and I'll find the ones that were presented at what was it? The 1-0 conference. There were like a ton of sport betting groups there, and
Okay.
then yeah.
Yeah.
Do we
I
need
didn't
to
even
go
know we
back to
had
the
like a
main
sports
room?
engineering major. That might be something I look into.
Send me a
We'll
message.
see.
I'm the second ever cohort. This year is the third.
Okay.
So I can tell you to contact. We are being fought over right now between mechanical and sticking in MSc and COE. I don't know, it's a lot. But
Okay.
I can tell you who to talk to if you're interested in it.
Okay, yeah.
Yeah.
Sounds
But
good.
also, if you didn't know, Indiana boasts now the largest sport tech ecosystem in the world.
What does
If
that
you
even
go
mean?
Yeah, so Indiana's pushing to be like this epicenter of sport tech, and they're bringing in all of these sporting companies
We have only
for
5 seconds.
Oh yeah, we have two
for
seconds. Okay.
Yeah, we'll be
Zach, I'll send you an email and with the answers to those questions.
Okay, thank you.
Yeah, you're welcome.
Have a good day.
Fantastic presentation.
Yeah, thank you.
Mhm.